This is Laboratory 2. We'll divide it up into two separate videos. The first will deal with the data collection and the data variables themselves, and the second will deal with the discussion of those. So for Lab 2, you're supposed to look into FOX 1.3A and B, and then also FOX 8.4A, B, and C. There's a number of reasons you might want to pay extra close attention to this. But one of them is there are possibly 5 laboratories you can write up from this experiment, which literally includes all 5 of them, plus the plasma values from FOX 2.1, which is in Lab 3, you can also do for your lab report. So one of these 8 little labs is one of the labs you need to choose for your lab report. So pay attention to these and kind of decide which one you want to spend a little more time looking at. So Lab 1.3A looks at homeostasis. Really, it looks at a concept called negative feedback, and it doesn't have much to do with homeostasis, to be honest. But we'll kind of go through why that is. So the idea was a water bath is basically a device in the laboratory that you set the temperature and put water in it and then turn it on, and it'll bring the water temperature up to that temperature, and then once it gets there, it'll shut off. So as the water cools to the room, it'll turn back on. It'll keep that temperature regulated, as this one is set in this picture as 23.2. So what we would do in lab is we have a water bath we would set to approximately 50 degrees Celsius, and the way we would measure this is we actually have a thermometer that sits inside the water bath. Our water bath would have a cover so that the temperature stayed constant or relatively constant, and the heat did not dissipate to the room very easily. So we would set the water bath to what we believe is 50 degrees, and what happens is it has a little light here, and when the light is on, it tells us the heater is on. When the light goes off, that means that the water bath should be at the temperature that we designated at. So the idea would be to turn the water bath on, wait until the light went off. When the light went off, then you would measure it for 5 consecutive times. You would then add ice to the water. That would drop the temperature. The light would go back on, and the light would stay on until it reached temperature again. And the idea would be to measure how low did the temperature go, and then how long did it take to get the temperature back to the normal temperature. So normally in class, if we were in class, we wouldn't do this portion of the lab because it's hard to do effectively with as many groups as we would have. We could probably do it on a smaller scale, but it just may not work as well. So what we would do is we would use the data presented right here. So we would turn on the water bath at the beginning of the lab, and it would take a while to heat up. And when it got to 50 degrees, the light would go off. Once the light goes off, then you would measure the temperature. We got these temperatures, 49.7. This is in degrees Celsius. Since we're in science, we should do degrees C if we can. And then 49.8, 49.8, 49.8, and 49.9. Sometimes students go, well, the light went off, yet the temperature is still going up. Why is that? The heating element has shut off, but it's still dissipating heat to the environment, right? It's sort of like a stove, right? You know, you shut off a pan, the pan isn't cool right away. No, I didn't mean to do that. So those are the temperatures. Then what we did is we took a fairly large amount of ice water, which is one of the reasons why it took so long. And that was out of the water bath, which dropped the temperature down to 37.6 degrees. Okay, so we went from an average of 49.8 down to 37.6. So we dropped, what, over 13 degrees Celsius. And then it took 47 minutes for the temperature to return to the average temperature, about 50 degrees C. So that's the data you would use for this portion of the experiment. One of the things that we'll talk about later is how well does a water bath mimic the homeostatic control of human body temperature. It's not a bad connection to look at that. And what's the difference between the water bath and homeostasis? As an example, our body temperature fluctuates typically in what they call a diurnal cycle, diurnal variation. So day-night, basically, is what diurnal means. And we see that the temperature goes up and down based on whether the lights are on and off. So what the water bath does is the water bath does a similar thing where the temperature goes up and down based on the set point. All right. So the problem with the water bath, though, is there's what they call no antagonistic control, and we'll talk about that in the discussion portion. Part B, right? So this is still FOX 1.3, so you should be in the FOX manual 1.3 looking at what they ask you to do. We measure pulse rates. And the idea is, and I want you to do this at home, is I want you to measure your own pulse. Now, since we're measuring your own pulse, you can measure with your thumb, because your thumb has a pulse. And if you're measuring somebody else's, if you get the corner of your thumb, which has a little tiny artery in it, and push against their tendon, you could feel your own pulse and not actually measure their heart rate, but measure your own. There's a bunch of ways to measure heart rate, and probably the most accurate, most standard is to count for 15 seconds. And since we usually report it per minute, then you multiply it by 4. So one of the things I want you to do at home is I want you to just pull out, something with a second hand, whether it's your phone or a clock or whatever, and we're going to change it a little bit. I want you to take your pulse rate 5 different times. Measure how many beats it is in 15 seconds, so put that number here, and then what's the per minute, just multiply by 4. So let's say you got 15 seconds, right, the first time. Let's say 15 beats, right? So 15 times 4 is 60. Then you got 17 here, right? That would be 68, and so on. And you just put all of them here. Then I want you to take your average heart rate. We're not going to obviously put something on the board, but the idea is take your average heart rate, and that would be considered your resting pulse. Now, that's not technically correct, but it's pretty good. And then what we would do in class is, okay, do you consider yourself a regular exerciser, somebody who exercises at least 3 times a week for 30 minutes, where you get your heart rate up high enough where it's difficult to talk? And you just decide, am I in the first column or the second? Okay? And we'll kind of look at some data from that a little later. We won't go through it now. We'll stay with what the slides say. We'd also do the 8.4 of FOX, which is really looking at acid-base balance and the role respiration plays in that. But it's a nice little experiment to look at a little bit of chemistry. So this kind of relates to the chemistry portion of the class. So what we would do in this section is, while we sort of follow FOX, he does not do a great job of controlling this experiment or allowing us to be able to look crossways at the experiment. So I've changed the protocol a little bit, and that protocol is in the lab supplement. This makes it much more scientific. If you read FOX, and he's changed it a little bit, but he used to say grab some water, put it in a beaker, measure the pH, and then drop 1 drop and 3 drops of HCl. The problem with that is pH is a measure of the hydrogen ion concentration. So if you had a gallon of water or a couple liters of water versus 10 drops of water, the pH would be drastically different. So we're going to grab 50 mils of fresh water, and fresh water should have a pH of 7.0. There are some contamination factors that if you didn't clean the beakers well, but theoretically you should be pretty close to 7. So you'd measure the pH, and then you'd put a drop of HCl in the water. Now HCl hopefully you recognize as an acid. If you've already looked at the chemistry video, you know that acids, bases, and salts dissociate, break up in water solutions because they're held together by ionic bonds, and that's going to give us an H plus and a Cl minus. Now, when we have an H plus, the pH is a measure of the concentration of H plus. It's actually 1 over the log of the concentration of hydrogen ion, right? And so the pH will drop significantly with 1 drop. For most people, it drops down to about 2.0. All right, so for the next part then, you're going to go ahead and add 2 more drops, so that's 3 drops total, and measure the pH. Now, since I put more acid in it, because HCl, hydrochloric acid, will drop pH, the pH will drop even further. But it doesn't drop nearly as much, even though you have twice as many drops in from the first time. And so usually the pH goes from like 2-ish down to like 1.5 or so. Then you take another beaker that's cleaned and washed, and you're going to put water in it. You're going to measure the pH, and it should be 7.0-ish. And now we're going to put NaOH. NaOH is sodium hydroxide, right? That's a base. What happens is it also, like acids and salts, bases dissociate. It's going to break up into Na plus and OH minus. And what happens with the OH minus is it basically sucks the H plus out of the solution. And as it removes the H plus out of the solution, the pH goes up. So 1 drop of NaOH typically goes to 10 or 11, and then, let's say it was 10.5, and then 2 more drops of NaOH to make 3 total would then take the pH farther towards the end in the more basic range, and it might go from 11.5 to 12. All right, so it really depends on a number of factors, but that's typically what we see for that. Now what we're going to do is we're going to do the exact same thing, except this time instead of using water, we're going to use a buffer. All right, so we're going to take the buffer at 7.0, and it's calibrated to and manufactured to be 7.0. So we'd expect the pH to be 7.0. And now instead of using water, we have buffer, and we're still going to do 1 drop and then 3 drops. When we put the 1 drop of HCl in, it drops a little bit, but it doesn't nearly do what it did before. So here we went from 7 to 2 with water. With the buffer, it goes from 7 to 6.8, 6.7, 6.6. It doesn't drop very much. It still goes down, but not nearly as much. And then 3 more drops takes it down to like 6.1 or 6.2. So pH, right, with 3 drops in water goes to like 1.5. pH with 3 drops in buffer goes to like 6.2. So not nearly the same degree of change. When we do it in the NaOH, same thing happens. We go 7 and pH goes up a little bit, maybe 7.4 or 5. And then oftentimes when we put 2 more drops in, the pH jumps up to like 11 or 12 again. And so you get sort of this weird data point here that we'll explain in the discussion, but for many people it jumps way up. Now, when we do this in class, I ask the class to do 8.C first, and the reason being is 8.4B asks the person to exercise. And what we're trying to measure is and you saw in 1.3b the resting pulse, so we don't want you exercising yet. And then in 8.4c, We want resting respiration, basically. And so once you've exercised, we don't have that resting respiration. So what I ask you to do is measure the breathing rate, and it's hard to do it yourself at home. You can do this portion of the experiment as well if you want, but I'd be very careful with this part, because if you hyperventilate, right, some people hyperventilate so vigorously they faint, right? So what you do is you just measure your breath, your breathing rate for 30 seconds. Now, one of the questions might be, why did we measure it for 15 seconds for pulse, but we're measuring it for 30 seconds for respiration? And, what do you expect someone's average pulse to be? I mean, I gave you an example of someone who's like measured, 15 the first time in 15 seconds and then 17 a second time and so on. So their average pulse would be, somewhere between, we expect most people in the class between 50 and 100, right? That's most we'll get. And most people are in the 70s and 80s, with some people in the 60s and 50s and 90s and so on. Occasionally get somebody that's really high or really low. But for the most part, you're talking somewhere in the neighborhood of about 70 or 80, 60, 70 or 80. Now, when we look at respiration, what do you expect respiration to be? All right, you got any ideas? Think about it for a sec. Respiration is supposed to be somewhere between 12 and 20 for most people. So typically a third of the frequency for that. And because respiration is relatively slow, you want to measure for a longer period of time. Because if you miss, something at the beginning and the end, and then multiply it by 4, you can be off by 8 respirations very easily. So counting for 30 seconds and then multiplying by 2 is usually the standard for respiration. So you want to get a resting respiratory rate somewhere between 12 and 20 for most people. Then you're going to have the person hyperventilate. They're going to take 4 to 5 deep, rapid breaths. So it'll sound like, you don't want to do that too long, because if you do it too long, you can faint. All right. And if you're trying to count somebody else's, it's kind of difficult. But we're not counting the hyperventilation. As a matter of fact, by definition, hyperventilate means to increase breathing, actually increase breathing more than you need for your metabolism, the way it's intended. So once you're done hyperventilating, you're going to measure the breathing rate again. And we're going to do the same thing we did before, count for 30 seconds and then multiply by 2. Now what's interesting about this part of the experiment is some groups, very few groups, go down. So they might, have 16 as a respiration rate and then 14 or 12 after. Some groups don't change, so they have 16 at the beginning and 16 after the hyperventilation. But most of the groups, more than 50% typically, and sometimes, 5 out of 6 groups, increase their breathing rate. They might go 16 to 18 or 20 or even 22 breaths per minute. And so we'll talk about why that happens and how to explain such disparate results. So why do some people get one thing and some people get the other? And we'll talk about what's happening there. The last experiment is actually 8.4b. Remember, we did C before. And again, you want to do this one because this is going to require somebody to exercise. And what you're going to do is you're going to get 2 beakers of water. Make sure they're clean, and what I have students do is I actually have them roll a little buffer around in it and then rinse the buffer out really well, and that'll neutralize any acid or base that's residual in the beaker from other experiments. Then what we do is we put 100 mLs of water into 1 beaker. Okay, so we're going to start with water. Then we're going to add 2 mils of what's called 0.1 normal NaOH. This, compared to the NaOH we use in the first part, is a really, really weak base. What it's going to do, it's going to take the pH from 7, right, because we just have water, up to about 8 or so, maybe 8.5, certainly probably not as high as 9. Now remember when we did the concentrated NaOH in the first part of the, the experiment in 8.4a, pH jumped with 1 little drop of, and in chemistry, most chemists, consider a drop like a 20th of an ml. So, now we're adding 2 mils of this really weak NaOH, and the pH just goes up a little bit. Then we add, a couple drops of what's called phenolphthalein. Now, phenolphthalein is an indicator, you probably remember it from chemistry, that is pink in basic solutions but turns clear in neutral or acidic solutions. So our solution, which has distilled water, it has NaOH, a base, which should increase the pH. So when we put in the phenolphthalein, it should turn pink. All right? Then we're going to mix it equally. And then what you do is you split that sample between 2 beakers. So you have 50 mils in each. And the reason why you do that is now we know that any difference between the 2 beakers, anything difference that happens, is not due to the mixing of the solution. We mix the solution as one uniform solution and then divide it into equal amounts between 2 beakers. So that controls for the solution. If you had to make it each time, you'd have to be really careful about measuring the exact amount of NaOH and water and even phenolphthalein to make sure that wasn't going to affect your experiment. So by mixing it once and then divide it into 2 beakers, and to have a pre and a post exercise one works pretty well. Okay. Then you're going to take a straw like you'd get at McDonald's or somewhere like that, and you're going to blow bubbles into one of the solutions. And as you blow bubbles into the solution goes to a lighter pink until it actually turns clear. And you're going to measure the amount of time that takes. Now, this is not really difficult, but what your job is during that expiration is you're only measuring when the person's expiring. And the person who's participating, their job is to try to expire at the same rate before and after running or cycling or whatever they decided to do to increase their heart rate and their metabolism. So, most people, when we try to mix this in class, we get most people somewhere between 15 and 45 seconds, with about 30 seconds being fairly ideal. You don't want to have it too fast, because then there could be, small changes that you may not be able to see in a short time when you can see it more easily in a longer time. And you just don't want it that long, because you just don't want the person to be blowing through a straw for 3 minutes and pass out or something. They wouldn't really, but that amount of time works nicely. I'm in the wrong spot there. So then you'd go on your exercise, and you'd exercise just about 1 to 2 minutes where your heart was high enough or it was difficult to talk. For those of you that exercise and kind of pay attention to heart rate when you exercise, for most people that's a heart rate of about 120, 130, not really, too difficult. Then you come back and you do the exact same thing, obviously in the new beaker that has the other half of the solution in it, and you look to the time to color change. Now, we expect time to color change post-exercise to be half the amount of time, or up to 80%. So somewhere between 50 and 80% what the original time was. And basically, we'll talk about the reasons why, but that's what we expect. So maybe we expect somebody at the beginning for 30 seconds pre-exercise and 22 seconds post-exercise, or something like that. All right. So, this kind of looks at the different experiments, a nice summary. For the water bath, we'll use the supplemental data, although we're going to do that for all the experiments this semester, right? For the most part. Does it mimic the human homeostatic system? We'll answer why or why not. Pulse rates, right? Everybody measures their pulse, and you take your pulse on yourself and your lab partners, and they go back vice versa. So then you get an average pulse, and you put that on the board based on whether you believe you're an exerciser or non-exerciser. You add acid to water, monitor pH, and then repeat with base, and then you add base to buffer. She should be acid to buffer and repeat. Measure the normal breathing rate for CO2, hyperventilate, and then measure it again, and then prepare that weak basic solution with phenolphthalein, blow bubbles until it turns clear, exercise, and then do it again. Okay, so that takes care of the data and kind of procedure, and we'll come back with another video on the discussion.